Hello students. In the last video I explained how to design a monostable multivibrator by using a timer IC, that is 555. In this video I am going to explain the designing of a stable multivibrator, both asymmetric and symmetric multivibrator using 555 IC. Now assume that we are designing a stable multivibrator. Now before going into the designing process, what is a stable multivibrator? A stable multivibrator is a circuit which has no stable state. In the monostable, we had one single stable state, but here the multivibrator will not remain in the stable state. It will switch between 1 and 0 continuously. That's why it is called free running oscillator. So we are going to design this oscillator or a stable multivibrator with a frequency of 1 kHz and duty cycle equal to 60%. So if I convert that into time, 1 kHz, that is 1 millisecond. So duty cycle is given is 0.6. So as you know, the formula for duty cycle is this. So this is given. So we have to find out what is the on period and what is the off period required for a 1 kHz free running oscillator. So if I substitute here the T on plus T off, that is T on plus T off equal to 1 millisecond, I can find out T on. That is T on is equal to 1 millisecond multiplied by 0.6. That is 0.6 millisecond. So if this is T on is 0.6 millisecond, T off should be 0.4 milliseconds. We come to know about these two. Now using these two formulas for a stable multivibrator, we have to calculate the resistor values given required. That is T on is a known value. Capacitor we can assume as 0.1 microfarad, and RA and RB we can find out easily. I'll start with this formula, that is T of is equal to 0.693 RB into C. So where RB is the only unknown parameter, I can substitute for C equal to 0.1 and this T of is equal to 0.4 millisecond. I'll get the answer as 5.7 kilovolt. Now going back to this formula, I can substitute RB, C 0.693 here as constant and T on equal to 0.6 millisecond. I'll get a value of RA equal to 2.8 millisecond. 2.8 kilo ohm, sorry. So now we will design a circuit for this. So I'll start with a new design. I'll bring one IC 555 which is available in the mixed virtual group. Mixed virtual groups. I have a 555 IC then. I'll bring it. I need one 555 IC. I also need resistor and capacitor. So I'll go to basic, then choose the resistor. Anyone you can choose there. Okay, I'll choose this resistor here. I'll place it. I need one more resistor. I'll place it over here. Then I need a capacitor, two capacitors. Two capacitors. Then I need a power supply and ground, so which I will select here. So power sources, you can choose the voltage source here, that is VCC. I think better we will go with the DC power. I'll place it over here. Then there is a ground. I'll place it here. Now we will start the connection. Before that, let me rotate these resistors. I'll place it properly. This capacitor again. Okay, so I'll connect this to the resistor. This is the junction. Let me drag it a bit. This resistor also. Connected. Now the reset pin number 4 connected to the VCC, which I am not using. This charge pin should go to this junction. Short, trigger and threshold. That is pin number 6 and 2. We need to short this one junction so that I can connect this to the resistor and capacitor junction here. Control pin connected through a capacitor to the ground. Pin number 1 is connected to the ground, that is the ground pin of IC 555. This is again connected to the ground. So this should go to the supply number 8 VCC. This is also connected. Now we will set the values, because now I got the values as here we got the values for resistors RA as 2.8 kilo ohm and 5.7 kilo ohm. So let me set the values. 2.8 kilo of period 5.7 kilo ohm. We assumed the value of the capacitor as 0.1 microfarad. This is 0.01 microfarad. So we will observe the waveform of this free running oscillator by using the oscilloscope, which is present over here. So I'll bring it, connect the output to this, and the other end of this the ground. I also want to watch capacitor charging and discharging process, so let me connect this here, this one to the ground. So we will save the circuit first before proceeding. So let us say Astable Multivibrator. It is saved here as Astable. Fine. Let me check the analysis in this one. Let me make it point. I think before the setting this value, I think better we run the simulation. Let us check the waveform whether we are getting the output or not. Yes, we have to set this properly. Okay, something is not proper. I think on period is more, off period is very less. So let me stop this. Okay, so I'll run this again. I'm getting more on period and off period. That is because instead of giving 2.8, I have given 28.8. So let me correct this. You run it again, check the timings. Okay, now if I check the on period, if it is matching, it is perfect. Yes, it is 0.577 millisecond, that is the on period. The total time period which you can notice here is around 1 millisecond, which is matching with my design, and this is 397 microsecond, which is equal to 0.4 millisecond. Now it is matching. So this is asymmetric stable multivibrator. It is called asymmetric monostable stable multivibrator because the on period is not equal to the off period. So here on period is more and off period is bit less. And this second waveform, this channel B, also this represents actually the charging and discharging of capacitor, which we have connected to channel B. And the voltage is always between 1/3 VCC to 2/3 VCC. Just see the voltages over here. This is around 8 volts and 4 volts. So that is, my VCC is 12 volt, and 1/3 of that is around 8 volts, and it's 4 volt, and 2/3 of the VCC is equal to around 8 volt. That is this point and this point. Now we will design a symmetric multivibrator. Now I'll go to again the description of that circuit. I'll explain the designing procedure. In the symmetric stable multivibrator, the duty cycle should be equal to 50%. That is, on period and off period are same. That is 0.5 millisecond. And formula for both are also same here. That is 0.693 RAC and 0.693 RBC. So assuming capacitor C equal to 0.1 microfarad, we can calculate RA, and RA should be equal to RB because the on period is equal to off period. So it comes out to be around 7.2 kilo ohm. So the same changes we have to make in the circuit also. In the circuit, we have to change this to 7.2 kilo ohm, and this is changed to 7.2 kilo ohm. and we have to include one diode. So let me place that component in the diode. We'll go with the diode. I think I can check that 1N4001 IC. Okay, I have it here. I'll place it. I'll rotate this diode. Okay, we have to connect this across RB. Now the capacitor will charge through R1 through the diode and the capacitor, and discharging will happen through the diode and discharging will happen through the resistor R2 through this pin. So RA is equal to RB. Let me check the result. Here RA should be equal to the on period should be equal to the off period. So this is on period, which is around 0.5 millisecond, and off period is also around 0.5 millisecond. So it's closely matching, and total time period is also equal to around 1.05 millisecond. Designed time constant is 1 millisecond. Now this is about the symmetric astable multivibrator. Now we can change the duty cycle here itself. This is a 50% duty cycle what we have designed. We can make it say less than 50% duty cycle. In the previous example, the duty cycle was 60%, which is more than 50%. Now it is 50%. If I change the value of this resistor, say I'll make it roughly 10K here. In that case, duty cycle will change and it will be less than 50% now. Just check, on period is smaller and off period is larger. So the duty cycle should be less than 50%. If you want to design with a duty cycle say more than 50%, we can do that one here itself. So let's say roughly I'll take 15 kilo ohm resistor. Now just check the output waveform. It is more than 50% because the on period is more than the off period. As you can see over here, the on period is more than off. 60% duty cycle astable multivibrator can be designed with this circuit also. Thank you.